Hello, we are starting to look at the programs that are described in the book, and we are looking at the GitHub repo for those programs. The programs start at chapter 3, so we will start with chapter 3. Chapter 3 demonstrates how to work the basics of the DEAP library, DEAP, and we use a sort of a toy problem that's called the 1max. The 1max, we have a string of ones and zeros, and we want to find the string that will maximize the sum of the digits of the string. So obviously to us it will be when all of them are ones. The genetic algorithm that we're going to use to solve it, a genetic algorithm in general is not aware of the internals of the fitness function. It's like a black box. It only knows what goes in and what comes out, so it finds a solution based on that. So let's look at the three programs. I have them here running on Windows in Visual Studio Code. Of course, you can use any IDE, or you can just use an editor, or you can just use the command window to run programs. Please watch the first video that tells you how to set up your environment and the libraries. And I'm just continuing from there. So I have a venv here, as you can see, which is a name of the virtual environment. It is installed with Python 3.12, so I will be running, when I activate this environment, everything will run with Python 3.12 and with the libraries that, all the libraries basically are installed already in that venv using the requirements file, like we saw in the original first video. So to activate it, when I use Visual Studio Code, I like to use this extension that's called Python Environment Manager, and I can see this environment there, and I can start a terminal with this environment. As you can see in green font here, it tells you that environment is activated. When I go now and open the chapter 3 program, this is my local clone of the repository, of the GitHub repository that we just saw. There are three programs that solve the problem. So what are the differences between them? Well, the first program is called long, and what this program does, it solves the problem of the 1max using the DEAP library. So it uses the constructs of the libraries, like the library, like the creator and the tools. But it implements the main genetic flow from scratch, basically written, the entire algorithm, the entire flow is written here in code, which gives us a lot of flexibility, but it's more work, I guess. And at the end, it plots, it prints the best solution, and it plots. So let's see the run and the results. And let's run it here. And when the program starts, it actually runs very quickly, as you will see. And it prints for each generation, it prints the best individual of that generation, as you can see if we go up there, and it prints the max fitness of the generation and the average. And we can see that the best individual has more and more and more ones as we go down the generations, and eventually after 40 generations it finds an individual that is all ones, and the fitness is 100, which is the most we can do in this case. And we had in the code, the code will stop when you reach that fitness, because we already know this will be the max fitness. And if we don't, when we don't know what is the max fitness which we expect, which is the usual case, we don't know, we will just run it to a fixed amount of generations, or until we don't see improvement for a long time, or all kind of other ways to decide when to stop. So if we go to the second program, let's kill this terminal, and let's look at the second program, and let's compare it to the first program, see why it's called short versus the long. And what we see is that the difference is, if we do compare selected, mainly that we use, instead of using, we now use the algorithms, the built-in algorithms of DEAP, and this whole code that we implemented before manually to run the algorithmic flow is now replaced with mostly the call to the EA simple, which is a built-in algorithm that DEAP offers us that basically does that. And we also use a statistics object and a logbook, which reports the results during the flow. And at the end, we can use that to extract the best individual. So instead of doing it manually here, we will have it by using the logbook. So when when we run this, we will see that generally speaking, we will have similar results. We did not really look at the graph before, but this graph is very similar. What you see here in red, you see the best individual in every generation, and you can see that it improves in jumps. Every so often it jumps up and we find a much better individual or somewhat better individual, and then it can stay for a while without improvement. So we get this jaggedy graph, and we know that after 40 iterations, after 40 generations, we found the best individual. Here we continue to 50 generations, so there is no improvement after that. The best individual is going to still be giving us 100, as you can see here. So there is no improvement, but the average keeps going up because more and more other individuals are becoming like that. So the green plot is the average fitness of the generation. You see this is much smoother and steadily growing in this case. So every generation in average is better than the generation before, until it comes to the point where there is no more improvement. So lastly, we have another program there. Let's look at that. And this program is called HOF. It's the same as the short, but we added HOF. HOF stands for Hall of Fame. DEAP has this feature called Hall of Fame, where over the generations it will put into this Hall of Fame the best so many individuals. So we define the size of it. So we can say the HOF size is, well, I don't see it. Here it is. The Hall of Fame size is 10, so it will keep, in this case, the 10 best individuals, and whenever there is somebody better than one of them, it will be replaced, and it will sort it always to have the best one on top. So this way we will not lose those, because during the generation you could lose a good individual once it gets crossed over with another individual, or it gets mutated. It might be lost of the population, so you don't want to completely forget that individual. So at the end you just look at the 10 best that you had ever. And we will see later that there is a way to actually maintain those individuals in the population called an elitist approach, but we are not doing it here yet. We're just using the Hall of Fame. So if we compare these two programs, let's compare them quickly. We see that we have that Hall of Fame constant, and then we inject this Hall of Fame, or we use this Hall of Fame argument, which is optional for the algorithm, and what we send there is an object that's called Hall of Fame out of the tools, which we use with the constant to give the size, and at the end we can print the Hall of Fame individual, or the best ever, which is the first individual in the Hall of Fame. So if you run this, we'll have exactly the same results and the same graph that we had in the previous run, because it's really the same program. But see, this is identical, but at the end we printed here all the individual, and you can see that the best individual, the top one, is the one that has all ones. Then the next one is one that has a 0 here, and then could be another 0 there, etc. So this is the use of Hall of Fame. So this is what I wanted to show you with chapter 3. We will continue in the next video with chapter 4.